Okay, so today, before coming back to Fredholm operators, we discuss, we'll make a short digression into the Banach space theory, and we discuss topological direct sums and complemented subspaces. So first of all, let's introduce some notation. Suppose we have two normed spaces, x0 and x1, and a real number p, which is greater than or equal to 1, and is not necessarily finite. And we define the LP direct sum of our spaces to be the following space, which we'll denote it like this. So as a vector space, this is just the direct sum of x0 and x1. And we equip the direct sum with a norm, where the norm is given by the following formula. So we'll take the sum of the pth powers of the norms and take take the power 1 over p. And this is if p is finite. If p is finite. And if p is infinite, we just take the maximum of these two norms. So clearly this is a normed space, and it's a simple exercise to show that actually each two norms from this family are equivalent to each other. So they are different, but they are equivalent. And each of them determines the product topology. Each of them determines the product topology on the direct sum. Okay, so now let's suppose that both x0 and x1 are vector subspaces of some normed space X. So suppose that X is a normed space, and that x0 and x1 are vector subspaces of X. Then we say that X is the topological direct sum, the topological direct sum of x0 and x1. And we use the following notation. If the following map from, let's take the L1 direct sum of x0 and x1, and let's consider the map from the sum to X, which takes each pair, x0, x1, to their sum. And we say that X is the topological direct sum if this map is a topological isomorphism. So for convenience, let's denote this map by star. Well, let's observe that, in fact, this map is always bounded because of the triangle inequality. And it is an algebraic isomorphism, if and only if x is the algebraic direct sum of x0 and x1. So as a result, we observe that, this is our first observation, that x is the topological direct sum of x0 and x1 if the following two conditions are satisfied. First, x should be the algebraic direct sum of x0 and x1. This means that this map is an algebraic isomorphism. And second, there is a constant c such that we have a following kind of inverse, kind of converse to the triangle inequality, such that for each x0 in the first subspace and each x1 in the second subspace, the sum of their norms is less than or equal to c multiplied by the norm of their sum. Well, indeed, this is equivalent to our previous definition, because the condition 1 means that this map star is an algebraic isomorphism, and condition 2 means that the inverse map is continuous or cumulatively bounded. Okay, and also one more simple observation. Since all these norms are equivalent to each other, we can replace in the above definition the L1 sum by the LP sum for each P. So the L1 direct sum can be replaced by the LP direct sum for an arbitrary P. It is convenient to characterize topological direct sums in terms of operators. So we will need the following simple fact from linear algebra. This is proposition 1. Suppose that X is a vector space. X is a vector space, and P is a linear operator on X. Then the following conditions are equivalent. Condition 1, P squared equals P. P is not important. And condition 2, there exist vector subspaces x0 and x1 in X such that X is their direct sum, and such that P restricted to x0 is the identity map, and P restricted to x1 is 0. And moreover, if the subspaces x0 and x1 are as in condition 2, then actually x0 is the image of P, and x1 is the kernel of P. Well, the proof is a simple exercise in linear algebra. So if P satisfies the above conditions, then we say that P is a projection of X onto X0. Such an operator P is called the projection of X onto x0 along x1. The projection onto x0 along x1. By the way, in Russian we usually say проектор. Не проекция, а проектор. Проекция — это результат применения проектора к какому-то вектору, а сам оператор чаще называют проектором. Okay, let's also observe, it's very easy but convenient, but useful, that if P is a projection, if P is a projection onto x0 along x1, then 1 minus P, where 1 is the identity map, is also a projection. And more exactly, this is the projection onto x1 along x0. This is more or less immediate from the definition. The projection, of course, it's unique. This easily follows from this two equalities. Okay, so let's now come back to functional analysis. One more simple property of topological direct sums. This is our proposition 2. Suppose that X is a normed space which is decomposed into the topological direct sum of two vector subspaces x0 and x1. And suppose that Y is another normed space, and T is a linear operator from X to Y. I claim that T is bounded, even only if the restrictions of T to each of the summands are bounded. T restricted to x0 and T restricted to x1 are bounded. Well, of course, the left-to-right implication is clear, so we have to prove the right-to-left implication. So we assume that each of them is bounded, and we have to show that T is bounded. Well, indeed, if we take an arbitrary vector in X, it can be decomposed as the sum of two vectors from the first subspace and from the second subspace. And if we now apply T to this vector, then by the triangle inequality, this can be estimated as follows. Now we know that each of these two restrictions is a bounded operator, so we can estimate this as a constant, say C prime, multiplied by the norm of C0 plus the norm of x1, where C prime is, for example, the maximum of the norms of these two operators. Okay, and finally, we look here. So we have a kind of converse to the triangle inequality for this direct sum. And so this is estimated as C prime multiplied by C and by the norm of x0 plus x1. And that's it. So this shows that our operator T is bounded. Okay. Okay, let's now characterize topological direct sums in terms of projections.
We said that this expression in the middle is just one norm in this space X. So it's just sum of norms of x0 and x1.
Yeah.
Can we say that it's as we define the P norm?
Well, this is not exactly the LP norm because we don't assume, let's look here, we don't assume from the very beginning that the norm of X is the LP norm. It's just a normed space with a pair of fixed vector subspaces. So it is equivalent. It is equivalent to the LP norm because of this, because of the definition. So if we assume that this is a topological direct sum, this means exactly that the norm on X, the original norm, is equivalent to the LP norm for some P, or for any P. This doesn't matter because all of them are equivalent to each other. But this is not an exact equality. This is an equality up to a constant. Okay, so let's now characterize topological direct sums in terms of projections. This is our proposition 3. Suppose that X is a norm in space. X0 and X1 are vector subspaces. And suppose that X is the algebraic direct sum of X0 and X1. Then the following conditions are equivalent. Condition 1, X is the topological direct sum of X0 and X1. Condition 2, the projection onto X0 along X1 is bounded. And condition 3, the symmetric condition, the projection onto X1 along X0 is bounded. Well, indeed, first of all, let's observe that condition 2 and condition 3 are equivalent because of that observation. So if P is a projection onto X0 along X1, then 1 minus P is the projection of X1 onto X1 along X0. So this means, this implies that 2 and 3 are equivalent. Let's now show that, for example, 1 implies 2. So suppose that X is the topological direct sum. I have to show that the projection P, so let P be the projection onto X0 along X1. I have to show that P is bounded. Well, indeed, if we apply P to the sum of two vectors, X0 and X1, from the respective subspaces, so this is by construction just X0. So the norm of X0 is, of course, less than or equal to the norm of X0 plus the norm of X1. And again, by the definition of the topological direct sum, or more exactly by this observation, this is less than or equal to the constant C multiplied by the norm of our vector. And this shows that P is bounded. Or by the way, it's also a special case of proposition 2. Yes, because clearly P is bounded on X0 and on X1, so it is bounded. Proposition, it was proposition 2 if I'm not mistaken. Yeah, proposition 2. And finally, to show that 2 implies 1, we observe that if you look at this map, which was denoted by star, then the inverse of this map of star is given by the following explicit formula. It takes each vector x narrow space to the pair p of x and 1 minus p of x. And so since p is bounded, so equivalently this means that 1 minus p is bounded, this readily implies that this operator is also bounded. So we conclude that star is indeed a topological isomorphism. Okay. Now, as a corollary, we see that if X is the topological direct sum of 2 vector subspaces, x0 and x1, then both x0 and x1 are closed. X0 and x1 are closed in X. Well, this is immediate from our previous result, because the image of a bounded projection is closed for the reason that it is the kernel of 1 minus p. So if p is the projection onto x0 along x1, then x0 is just the image of p, or equivalently the kernel of 1 minus p. And the kernel of bounded operator is always bounded. Is always closed, sorry. The kernel of a bounded operator is always closed because this is the preimage of 0. And the preimage of a closed set is closed. Now let's, so far we didn't assume completeness. X was an arbitrary norm space. Now let's suppose that X is a Banach space. In this case, we have the following result. So if X is a Banach space, and if x0 and x1 are closed vector subspaces, such that X is the algebraic direct sum of x0 and x1. I claim that X is actually the topological direct sum of x0 and x1. And to prove this result, we simply apply the inverse mapping theorem to our operator, which was denoted by star. So let's recall that star takes the L1 direct sum of x0 and x1 to X. So since X is the algebraic direct sum, this map is bijective. It is obviously bounded, and by the inverse mapping theorem, a bounded bijective operator between Banach spaces is a topological isomorphism. Okay. Let's now imagine the following situation. Suppose we have a Banach space or an ordered space X and a closed vector subspace X0. So the natural question is, can we always find another closed subspace X1 such that X is the topological direct sum of X0 and X1? Surprisingly, it turns out that in general the answer is no. And if such a subspace X1 exists, then we say that X0 is complemented in X. So we have the following definition. Suppose that X is an ordered space, and X0 is a vector subspace of X. And we say that X0 is complemented in X if there exists another vector subspace X1 such that X is the topological direct sum of X0 and X1. In Russian we say дополняемое подпространство. Well, of course, there is a necessary condition. If we look here, we see that each complemented subspace is necessarily closed. If X0 is complemented, in X, then it is closed. And there is an important special case in which this necessary condition is also sufficient. So we have the following example. If H is a Hilbert space, and H0 is a closed vector subspace, then we know that H is the direct sum of H0 and the orthogonal complement. This is the orthogonal complement theorem. And this implies that H0 is complemented in X. H0 is complemented in H. And moreover, the norm on H is exactly the L2 norm, L2 direct sum. If you take the L2 direct sum of H0 and H0 orthogonal, then the respective map is not just a topological, but is in fact an isometric isomorphism by the Pythagorean theorem. So all closed vector subspaces of a Hilbert space are complemented. And here's a counterexample which shows that for general Banach spaces, this is not the case. The exercise is not very easy, but a detailed hint is given in our second exercise sheet. So if we take the little C0 space, then it is not complemented in L infinity. This is probably the easiest example, but it is not easy. In fact, this phenomenon is not an exception, but is rather a general rule. In fact, they have the following interesting but non-trivial result due to Lindenstrauss and Safriri. Which was proved sometime in the 1970s. If X is a Banach space, such that all closed vector subspaces are complemented, then it turns out that X is topologically isomorphic to a Hilbert space. So the above example is essentially the only example in which all closed subspaces are complemented. So if you take any Banach space which is not topologically isomorphic to a Hilbert space, such as, for example, the little p space or the big L p space, where p is different from 2, or the little C0 space, or the L infinity space, or the space of continuous functions on the closed interval, then we can always find a closed non-complemented subspace in such a Banach space. The result is highly non-trivial, so of course I'm not going to prove it. But nevertheless, it shows the general rule of Banach space theory. So the non-complemented subspaces exist in abundance. Okay. Now, our next goal will be to give a criterion for a vector subspace to be complemented. So we have the following theorem. Suppose that X is a normal space, and X0 is a closed vector subspace. Then the following conditions are equivalent. Condition 1, X0 is complemented in X. Condition 2, X0 is the image of a bounded projection. There is a projection P, a bounded projection P on X, such that X0 is the image of P. And condition 3 is given in terms of quotients. There exists a bounded linear operator S from the quotient of X modulo X0 to X, such that S is a section of the quotient map, such that Q composed with X is the identity map of the quotient, where Q denotes the quotient map of X onto the quotient. Well, first of all, 1 and 2 are equivalent. We observe that 1 and 2 are equivalent by proposition if I'm not mistaken, this was proposition 4. I cannot find it on the blackboard. No, not 4. 4 is about Banach spaces. Yeah, that was proposition 3. It's not on the blackboard anymore, but the statement was that if x is the algebraic direct sum of x0 and x1, then it is a topological direct sum if and only if the respective projections, or at least, in fact, one of them or both of them, this is equivalent, are bounded. And this implies that 1 is equivalent to 2, because if x0 is complemented, then we take the respective space x1, such that x is a topological direct sum, and just take the projection of x0 along x1. And it will be bounded by proposition 3. And conversely, if x0 is the image of a bounded projection, then x0 is the topological direct sum of the image of P and of the kernel of P. Okay, so let's now show that 2 implies 3. 2 implies 3. So we look at the following picture. This is 1 minus P, x from x to x. So the kernel of 1 minus P is the image of P. So it is x0. So if we now quotient out the kernel, we have a well-defined bounded linear operator S, such that this diagram is commutative, because x0 is the kernel of 1 minus P. I claim that this is exactly the map we are looking for. Well, indeed, the diagram is commutative. This means that SQ equals 1 minus P. Now we apply Q once again on the left. So we see that QSQ equals Q minus QP. But QP is 0 because P is the projection onto x0, and x0 is precisely the kernel of Q. So this is 0. So we see that this is Q. And finally, we can cancel Q on the right because Q is surjective. And this implies that QS equals the identity map on the quotient. Okay. So this shows that 2 implies 3. And let's now show that 3 implies 2. Well, so now we have S, and we have to construct P. And this diagram suggests the way of constructing P. So P should be 1 minus SQ. So I claim that P is a projection, and the image of P is x0. To show that P is a projection, it suffices to show that SQ is a projection. Well, okay, SQ squared. What is this? This is SQ. But QS is the identity map. So this is just SQ. So SQ is idempotent, which means that it is a projection. SQ is a projection, and hence P is also a projection. Now the image of P, what is the image of P? The image of P is the kernel of SQ. But the kernel of SQ is actually the kernel of Q, because S is injective. And the fact that S is injective is immediate from this formula. This formula already implies that the kernel of S is trivial. So S is injective. So S is injective, and this means that the kernel of this composition SQ equals the kernel of Q. But the kernel of Q is, of course, X0. So we conclude that P is a bounded projection onto X0. And this completes the proof. Okay, now let's deduce a couple of useful corollaries of this result, which will be useful in our study of Fredholm operators. Corollary 1 states that all finite dimensional subspaces are complemented. Suppose that X is an ordered space, and that X0 is a finite dimensional vector subspace. Then X0 is complemented. To prove that X0 is complemented, we will use condition 2 for our theorem. So we are going to construct a bounded projection onto X0. So first of all, we take a basis in X0. So let E1 to En be a basis of X0. And we consider the dual basis of the dual space. Let, say, F1 to Fn be the dual basis of X0 star. So the dual basis means that, that if we apply Fi to Ej, we get the Kronecker delta. And then we use the Helm-Banach theorem, and we extend the functionals F1 to Fn to the whole space X. So we extend our functionals to functionals, say, F1 tilde, Fn tilde. By the Helm-Banach theorem. And now we can explicitly construct a projection onto X0. So we will now define P by the following formula. This is the sum from 1 to n. Fi tilde of X EI. So it's easily seen that P is a bounded projection onto x0. Well, indeed, if we apply P to, say, EJ, then by the choice of our functionals, we get the same, where is it? Because of this formula, we get the same IJ, we get the same vector EJ. So P is the identity map on 0, but on the other hand, the image of P is clearly contained in x0 because of this formula. So it is a bounded projection onto x0. And this completes the proof. And one more corollary of our previous criterion, corollary 2. I claim that all closed subspaces of finite codimension are also complemented. Suppose that X is an ordered space, and X0 is a closed vector subspace of finite codimension. Then it is complemented in X. Well, to prove the result, it will be more convenient to use condition 3. So we are going to construct a section of the quotient map. So x0 is a finite codimension. This means that the quotient of x modulo x0 is finite dimensional. So we choose a basis, say E1 to En. Let it be a basis of the quotient. And so our quotient map is, of course, surjective, so we take any vectors in the preimages of E1 to En. So for each I, EI is Q applied to xi for some xi in X. And now we define S from the quotient to X. So let it be the linear map defined by the following rule. So we simply define S on the basis and extend it by linearity. So it is bounded because the quotient is a finite dimensional vector space, and all linear operators from any finite dimensional normal space to any other normal space are bounded. S is bounded because the quotient is finite dimensional. And by construction, QS is the identity map. So our theorem implies that x0 is complemented in X.
We also realize this x0 as some intersection of kernels of some linear functions, or it would be more complicated.
That's true, but I don't see how this can help to prove that it is complemented. Because, well, if we well, it doesn't seem to me that this, well, of course, even if we want to prove that a codimension 1 subspace is complemented, we have to do some, we need some argument to show that this is true. Of course, this is true, but I don't think that this is easier than to prove that a finite codimensional subspace is complemented. But this is, of course, that is true. It is the intersection of finitely many hyperplanes. Okay, so that's all I wanted to tell you about complemented subspaces. And now we come back to the theory of Fredholm operators. So our next goal will be to prove the Nikolsky-Atkinson criterion, which characterizes Fredholm operators in terms of compact operators. So we'll discuss the Nikolsky-Atkinson criterion. And we apply it to study to our study of the properties of the index. So we have the following result, following theorem, which is due to Sergei Mikhailovich Nikolsky. If I'm not mistaken, this is 1943, and Atkinson, 1951. In fact, in full generality, this result was proved by Atkinson, and Nikolsky considered a special but important case of operators of index 0. So suppose that x and y are Banach spaces. X and y are Banach spaces, and T is a bounded linear operator from x to y. Then the following conditions are equivalent. Condition 1, T is Fredholm. Condition 2, there exists a Fredholm operator S, which acts in the opposite direction, that is from y to x, such that T as T equals T, and such that 1 minus ST, so this is the identity map of x, and 1 minus TS, so this is the identity map of y. So these two operators are finite rank projections. Finite rank projections. That is projections with finite dimensional images. Oh, well, if you don't mind, I'll continue on this blackboard. So that the statement will be easily seen. Condition 3, there exists a bounded linear operator S from y to x, such that St equals 1 modulo compact operators, and Ts equals 1 again, modulo the compact operators. So this abbreviation means that the difference 1 minus st, 1 minus st, and 1 minus ts are compact. And such an operator T is called an essential inverse of T. Any such operator T, operator S, is called an essential inverse of T. In operator theory, when we say the word essential, usually this means that some property holds modulo the of compact operators. So S is an essential inverse means that these two differences are compact. Property 4, there exist two operators, S1 and S2, from y to x, such that S1t is the identity map modulo the compact operators, and TS2 is the identity map of y modulo the compact operators. And it's natural to call such operators left essential inverse and a right essential inverse. Left and right essential inverses of T. Okay, so these four conditions are equivalent. But this is not the end of the story. Moreover, we have the following two statements. If, in addition, we know that the index of T is 0, if the index of T is 0, then we can always find a topological isomorphism. A topological isomorphism S from y to x satisfying condition 2. So it's not just a Fredholm operator S, it's a topological isomorphism between y and x. And finally, if the operators S1 and S2 satisfy condition 4, so S1 is a left essential inverse and S2 is a right essential inverse, then S1 minus S2 is a compact operator. So in our language, this means that they are essentially the same. They are the same modulo of the ideal of compact operators. So they are essentially the same, and each of them is a two-sided essential inverse. S1 and S2 are essential inverses of S. Of T. Moreover, they are automatically Fredholm. S1 and S2 are Fredholm. And the index of S1 and the index of S2 are equal to minus the index of T. Okay, so this is the Nikolsky-Atkinson criterion. So this result shows a nice relation between compact and Fredholm operators. So on the one hand, we have the Rees theorem, which states that if k is a compact operator, then 1 plus k is a Fredholm operator of index 0. And this is the continuation of the same story. This result establishes a nice interplay between compact and Fredholm operators. Okay, so let's now prove this result. First of all, we show that 1 implies 2. We assume that T is Fredholm, and we construct S satisfying 2. So, since T is Fredholm, this means by definition that the kernel of T is finite dimensional, and the co-kernel of T is finite dimensional. Well, or in other words, the image of T is of finite codimension. It is a closed subspace. We know that the image of Fredholm operator is closed. So the image of T is a closed subspace of finite codimension. We now apply our previous results, and we see that the kernel of T and the image of T are complemented subspaces. In X and Y respectively. So we can decompose X and Y in the following way. There exist decompositions of the following form. X is the topological direct sum of x0 and x1. And Y is a topological direct sum of y0 and y1, where x0 is the kernel of T, and the y1 is the image of T. And moreover, x0 and y0 are finite dimensional. x0 and y0 are finite dimensional. Because x0 is the kernel, and y0 is isomorphic to the co-kernel, to the quotient of y modulo the image. Okay. Let's now observe that if we restrict T to x1, let's denote this restriction by T1, then this map, this operator, is a topological isomorphism of x1 onto y1. This is a topological isomorphism by the inverse mapping theorem. Because it is bounded and bijective. Okay, so we now construct our operator S satisfying condition 2. To construct S, it will be convenient to draw a picture which explains how T acts. So this is the first space, space X. This is Y. This is X1. This is X0. This is Y0. And this is Y1. So T is a topological isomorphism of X1 onto Y1. This is T1. And of course, it takes x0 to 0, because this is the kernel. We now construct this. So first of all, we take an arbitrary linear operator from y0 to x0. Let S be any linear operator from y0 to x0. For example, we can take the 0 operator. And we define S from y to x in the following way. S is the direct sum of S0 and T1 inverse. S0, thank you. This is S0 and this is S. And so this is the picture. S0 is any operator from here to here. And we have T1 inverse here. So this picture shows how S acts. So clearly S is a bounded linear operator from y to x because the restrictions of S to these two topological direct sums are bounded. So the first map S0 is bounded because the space is finite dimensional, and T1 inverse is bounded because T1 is a topological isomorphism. So S is bounded because S restricted to y0 and S restricted to y1 are bounded. And it's clear from the construction that TST equals T. So we first apply T, then S, and then T, then we get T. Because this is true for on each on the summons. We have to show that, first of all, that S is Fredholm, and that 1 minus TS and 1 minus ST are finite rank projections. So if we look at, for example, ST, so what is ST? ST is the projection onto x1 along x0. So it takes x0 to 0, and it is the identity map on x1. So it is the projection onto x1 along x0, and this implies that 1 minus st is the projection onto x0 along x1. And so it's a finite rank projection because the image of this projection is x0, which is finite dimensional. Similarly, if we now look at TS, so what is TS? Well, TS is the projection of y onto y1 along y0. Again, by construction. It takes y0 to 0, and it is the identity map on y1. So this implies that 1 minus TS is the projection onto y0 along y1. And so it's a finite rank projection because y0 is finite dimensional. So 1 minus TS and 1 minus ST are finite rank projections. And to complete the proof of the implication 1 implies 2, we have to show that S is Fredholm. Well, to see that S is Fredholm, we observe that by assumption T is Fredholm. And we have just proved that ST is Fredholm. So T is Fredholm by assumption, And ST is the projection onto x1 along x0. So it is a projection with a finite dimensional kernel. So clearly each projection with a finite dimensional kernel is Fredholm. So T and ST are Fredholm, but some time ago we proved that this implies that S is Fredholm. So more exactly, when we proved the additivity of the index, we also proved that if you have two composable operators, S and T, composable means that the domain and the range are compatible. Then if we look at S, T, and ST, at these three operators, then if two of them are Fredholm, then so is the third one. So S is Fredholm. Okay, so this completes the proof of the implication 1 implies 2. Mm-hmm. Do you speak about ST or about which operator?
S.
S, well, S is... well, yes, this is also possible. S is, the kernel is contained in here. And the co-kernel, well, the image contains x1. The image contains x1, which implies that the image has finite codimension. Yeah. So instead of referring to our old result, we can just look at this picture. You're right. Okay, so if we now look at 2, it's clear that 2 implies 3 and 3 implies 4. Oh, by the way, before we continue our implications, it is convenient now to prove this statement. So if the index is 0, then there is a topological isomorphism satisfying condition 2. Well, indeed, if we assume, in addition, that the index of T is 0, so then x0 and y0 are of the same dimension. The dimension of x0 equals the dimension of y0. And so, since S0 can be an arbitrary linear map, but since the dimensions are the same, we can take an isomorphism between y0 and x0. There is an isomorphism S0 between y0 and x0. And this easily implies that S, which is the direct sum of S0 and T1 inverse, is also a topological isomorphism. Because each of the summons is a topological isomorphism. Okay. Now it's clear from our construction that 2 implies 3 and 3 implies 4. Because, well, finite rank projection is a compact operator. And so if S satisfies 2, then the same S satisfies 3. And of course, 3 implies 4. That's clear. If we have an accessional inverse, then S is both a left and a right accessional inverse. Let's now show that 4 implies 1. 4 implies 1. So, first of all, this condition, S1T, is the identity module of the compact operators. Explicitly, this means that S1T is 1 plus K1 for some compact operator K1 on X. So by the Ritz-Schauder theorem, this operator is Fredholm. So S1T is Fredholm. And this implies that the kernel of T is finite dimensional. Because it is contained in the kernel of S1T. Similarly, if we look at TS2, this is the identity plus the compact operator K2 on the space Y. Again, the Richardo theorem states that this is a Fredholm operator. So TS2 is Fredholm. TS2 is Fredholm. And we know that in this case, the co-kernel of T is finite dimensional. This was proved some time ago, but this can also be seen explicitly. If
How do we know that the kernel of S1 is finite dimensional?
the kernel of S1 is not necessarily finite dimensional. So far, we don't know that S1 is Fredholm. But at this point, we don't need this, because the kernel of T is contained in the kernel of S1T. And since the kernel of this operator is finite dimensional, this implies that the kernel of T is finite dimensional. Maybe this implication is less obvious, but we have proved this some time ago. So if composition of two operators is Fredholm, then the second one, namely T, has finite dimensional co-kernel. So if we now combine these two statements, we see that T is Fredholm. T is Fredholm. So this completes the proof of our implications. So we now see that all the four properties are equivalent. Now to complete the proof of our theorem, we have to prove this last statement. So we have to show that if S1 and S2 are left and right essential inverses, then they are essentially the same. Both of them are essential inverses, two-sided essential inverses. They are Fredholm, and the indices are equal to minus the index of T. So this is the last step of the proof. Okay, so now S1T is 1 plus K1. If I multiply this equality on the right by S2, we see that S1T S2 equals S2 plus K1 S2. And if we now take this equality and multiply it on the left by S1, we see that the same operator, S1T S2, equals S1 plus S1 K2. And if we now compare this and this, and take the difference, we see that S1 minus S2 is the difference of these two operators, which are compact. So these equalities imply that S1 minus S2 is a compact operator. Okay, but this statement easily implies that both S1 and S2 are two-sided essential inverses. Because, for example, S2T equals S1T modulo the compact operators. So S2 minus S1 is compact, so S2T minus S1T is also compact. But S1T is equal to the identity map modulo the compact operators. And this shows that S2T is a two-sided essential inverse. And the same argument applied to S1 shows that S1 is a two-sided essential inverse. So TS1 equals TS2 modulo the compact operators, because S1 minus S2 is compact. And this is the identity map modulo the compact operators. So they are essential inverses of T. Why are they Fredholm? They are Fredholm because we already know that conditions 1, 2, 3, and 4 are equivalent. And T is an essential inverse to each of them. T is an essential inverse of S1 and of S2. And since conditions 1 and 3 are equivalent, we simply apply them to S1, for example, and we conclude that S1 and hence S2 are Fredholm operators. They are essentially invertible. So they are Fredholm. And finally, we have to calculate the index. Well, we'll look again here. S1t is 1 plus k1. And again, by the Riesz theorem, this is a Fredholm's index 0 operator. So the index of S1t is 0. But this is, by the additivity of the index, this is the index of S1 plus the index of t. So we conclude that the index of S1 is minus the index of t. And if we apply a similar argument to TS2, we get the same result for S2. Similarly, we see that the index of S2 is minus the index of t. Okay, so this completes the proof of the Nikolsky-Atkinson criterion. Oh, that's all for today.